All right, so it's a great pleasure to introduce Cheltsov from Edinburgh, who going to
Scotland.
That's a political statement. But all right, so who's going to introduce us to G-birationality, rigid cubic threefolds? G-birational.
Okay, thank you, Emil. And okay, my talk will be very down to earth talk, very explicit, and it's a recent work with my former PhD student Igor Krylov, and from Korea, and Sianer Mao from. Okay, so let me start with reminding classical theorem of Clemens-Griffiths, irrationality of cubic threefolds through intermediate Jacobian. And approximately at the same time, they proved the theorem. Skovsky and Manin proved irrationality of smooth quartic threefold, but methods was very, very, very different. So basically, method of Clemens-Griffiths intermediate Jacobian, and which is actually only related to atoms in some sense. And you may think this is three-dimensional atoms back in the 70s. And the Skovsky and Manin, what they actually proved, they proved much more than irrationality. They proved that smooth quartic threefold is not birational to fibration into conics, fibration into Delpezzi surfaces, or fibration to any rational surfaces, or not birational to any Fano, mildly singular, with a class group of rank 1, which is not biregular to X. And basically, this theorem later became a definition of what is now called like birationally rigid. Yeah. And moreover, they also proved that group of birational automorphism coincide with the group biregular automorphism, and this is a finite group. So basically, any of these lines, this, or that, implies irrationality. So this is like very opposite side of rationality, very, very non-rich. And from some point of view, like say from atom point of view,
so this group could jump for some special part.
Yeah, but that's fine. If quartic is threefold, it's fine. Very more, but it's more monstrous.
It would differ from one.
But it's final. If it's rational, it's infinite. If birational, yeah. So it's but generically it's trivial, but it may be okay. Actually, it's a good question. So we don't exactly know possibilities for this group, which is somehow related to part of my talk. Okay, so essentially two different methods, and it was very tempting to apply different intermediate Jacobian method to quartic, and rigidity method of Skovsky-Manin to cubic. And okay, in one direction it's almost done. So basically, I think we still don't know that intermediate Jacobian of every smooth quartic field is not Jacobian of a curve, but for general one we know through the degeneration technique. On the other hand, Skovsky asked one of his students, Kashan, to basically try to prove something like this for cubic threefolds. You cannot prove this. I will explain in the next slide, but something like it. And basically, as a result, the students just left Mathematics. So it was much more difficult. And if you're interested why it's more difficult, we can talk during the break. Okay, anyway, so
how do you know it's not the default?
No, we don't know. That for what I want to say, intermediate Jacobian of quartic threefold don't analyze as well as cubic. But let's try to do other way around.
So there is no conic bundle.
Yeah, because there's no conic bundle, and but still there is some approach. Like for example, quartic double solid, double cover specific quartic also is not birational conic bundle.
That's Voisin.
But Voisin proved it. So what I want to say, there was some attempts also to do the same here. But okay, my essential idea of this talk is the idea of try to apply this theorem, this method to cubic threefold, despite the fact that we cannot do this. Okay, so this is basically proper definition of birational rigidity for threefolds. Fancy definition is that Fano, which is a Mori fiber space of a point, birationally rigid, if this is a unique Mori fiber space which is birational to this Fano. But for threefolds, it's basically very simple definition. You can rephrase it as Fano threefold with a class group rank 1 and terminal singularities. So these two conditions is a part of definition, which basically means it's a Mori fiber space over a point. That's birationally rigid if it's not birational to any fibration into Fanos, fibration to Delpezzo surface, conic bundle, and if it's not birational to any other Fano threefold with the same property, except itself. Yes. And if in addition these two groups coincide, we call it birational superigid. Okay, so cubic threefold is not birational. There are three independent ways to see this. The simplest way is basically you just grab a plane in P4 and you consider a linear projection from the plane and you restrict it to the cubic. So you take this curve, usually it's a smooth cubic curve, but it doesn't matter. You blow it up and this gives you fibration into cubic surface. Cubic surface is a Delpezzo surface. You basically obtain birational transformation into Delpezzo fibrations. So if this curve is smooth, this is just fibration whose general member is a cubic surface. But if it's singular, you can apply you can desingularize Y and then apply relative minimum model program. So you get at worst sometimes you get vibration into Delpezzo surfaces of degree 2. And okay. So it is not birationally rigid. Second example, second way, it's very similar. You take a line in X, and projection from the line gives you a conic bundle structure. So it means you blow up this line, you have conic bundle with discriminant curve from degree 5. So actually, which is actually was used implicitly by Clemens and Griffiths to analyze intermediate Jacobian, because a correspondent prime variety is exactly intermediate Jacobian. Okay, there's another way to see that cubic threefold is not birationally rigid, which is less known, but still very famous. It's actually was birational transformation found by Fano. Now we call it Sarkisov link. So it goes back to Fano. It was accurately rewritten by Skovskih and then by Petrucci and by many people. So basically, if one can show that smooth cubic threefold contains quintic elliptic curve, and if you blow up this elliptic curve, you don't get a Fano. This is what's called weak Fano, because every second of this elliptic curve, which is contained in a cubic, gonna intersect with anticanonical divisor of this Y trivial. So anticanonical divisor is going to be a big and nav, so it's like what's what we call weak Fano. And then you can flop these curves, and then you can contract some surface which on Y prime to threefold X prime, which is a smooth Fano threefold with the current 1 and anticanonical degree 14. And this pi prime is actually also blow up of smooth quintic elliptic curve. So this is like a classical Sarkisov link discovered by Fano long time ago. In particular, it shows another time that cubic is not birationally rigid. Okay, but we can make it to be birationally rigid if we consider some symmetries. So basically, we can just take the definition of rigidity and we just add action of a group. Okay, since we're mostly interested in finite group, let it be finite group and okay, but same works for algebraic. So basically, it's basically copy-paste of the previous slide. We take a Fano varieties with most terminal singularities. Now we fix some finite group, acting regularly on it. We assume that invariant part of the class group is of rank 1. So this is basically G-Mori fiber space over point. And we basically copy-paste the definition. We say that X is G-birationally rigid if it's not G-birational to any other G-Mori fiber space, which is not G isomorph to X. So it means no equivalent birational map into fibration into Fanos, and there's no equivalent birational maps into other Fano varieties with the same properties, which are not G biregular to X. And if on top of this, if these two groups coincide, we set as G-birational superigid. So this is basically a normalizer of the group G in the group of birational automorphism of X, and this is a normalizer of the group G in the group of biregular automorphism of X. Okay, and now with this definition, of course, cubic can be G-birationally rigid. So, okay, but first let me illustrate what we know about this property for surfaces. Surprisingly, this definition inspired implicitly Iskovskih and Manin to prove the quartic theorem. Because they basically, the idea of the irrationality of quartic theorem by Iskovskih and Manin were based on the old work of Segre and Manin about G-birational rigidity of cubic surfaces. But Segre and Manin consider this in arithmetic settings for the Galois group action. Basically surfaces of a non-closed field, but definition essentially the same. So, okay, let me state what is known about G-birational rigidity of Delpezzi surfaces. So we fix a Delpezzi surface, two-dimensional power variety, to be smooth, with singularity terminal in two-dimensional smooth, and we fix a finite group. We assume that rank of the class group equal to 1. Okay, first of all, I want to say that this all possibilities for X and G with this property are known. It's listed in the paper by Dolgachev and Iskovskih, famous paper called Cremona, finite subgroups of Cremona group. But actually, they list has minor discrepancies. So corrected list appeared in my paper with Zhizhan, who is here in the Yurichenko. It's on archive 2 weeks ago. So you can find all possibilities for X and G with these properties. Yeah. Okay, then X is G-birationally rigid. If you have, we can just go by the degree. If anticanonical degree is small, it's basically classical Segre-Manin theorem. So it's all of them are G-birationally rigid. And this is actually was, as I said, inspiration for the Iskovskih and Manin theorem for the quartic. And for degree 4, it's basically almost all such groups give you G-birational rigidity, except very few exceptions. For degree 5, it's only 2 groups which give birational rigidity. This is actually good exercise. And degree 6, it's an interesting story. I don't have much time to talk about this, but this is actually very recent. So all of this is kind of known. This is basically in our paper with Zhizhan and Yuri, which appeared 2 weeks ago. And all of these 3 parts of the theorem are absolutely very similar to what happened in the arithmetic set. Degree 6 in arithmetic settings results very different. It's a recent paper by Yesinsky and Kurz. And in arithmetic setting situation much more different, much more complicated. But in geometric settings it's very nice. Okay, and then you have P1 cross P1 and P2. So we have this very explicit, basically give you complete solution of this problem in dimension 2. And this is not just isomorphism of groups. You can list these groups. Each such group is unique. You can list its generator. So problem is totally solved. And again, it started from Segre and Manin. And the final things basically was done with this. Okay. Now, callers, this a bit partial inspiration for this project, not only for this project, for some other projects too. It's question of color, which is actually an original question was asked for the Galois group actions, but let me rephrase its geometric version. So you take a Fano threefold with terminal singularities, and now you fix 2 subgroups in the automorphism groups. And you assume that for both of them, this is a G-Mori fiber space. So it basically means rank of class, invariant part of class groups, 1 for both groups. And then if you think about this, so intuitively it's clear. If you prove H rigidity for the small group, it should imply rigidity for the big group, because the larger group, the less your geometry becomes more rigid. Yeah. So basically, this is the question of color. Suppose that X is H-birationally rigid for small group. Does this always imply that X is G-birationally rigid? Answer should be yes, but expected answer is actually no. In dimension 2, it's a theorem by Yesinsky. Answer to this question is yes. And Yesinsky proved it before classification, which I listed on the previous slide. So if you have a theorem on the previous slides, you basically just apply and you get the theorem. But Yesinsky did it a few years ago. And in dimension 3 and higher, we expect that this is not true. And yeah. And if you think about this, you can see the way how to try to construct counterexamples. Yesterday we had some informal workshop. I basically even suggested some counterexamples, but candidate, but we don't know yet how they are. So anyway,
But how could you prove that the answer is yes, but it is observed?
for the better surface,
Yeah.
okay, you can just go back. For example, suppose degree is 3. And all of them are rigid. End of proof. So suppose you take a 5. Okay, for this 2, it's rigid. If it's have a small, it's small.
Yeah, but with the list I agree.
Without the list. Implicitly, Yasinski, okay, it's a good story. You can find a geometric criterion to be rigid, like fixed orbits or small. You can do this. It still requires some partial classification, but not the full one. This is correct. Anyway, so this was a motivation, but why we don't yet have a counterexample? Because we don't have many examples of this G-rigid Fanos in general. So the more examples we have, the more we can try this question. So okay, so we tried the toric or Fanos in dimension 3, and then we decided to try cubic threefolds, basically. Yeah. Okay, and surprisingly for cubic threefolds, instead of trying question of color, we basically just found all cubic threefolds which are G-birational. And surprisingly, classification is very simple. So okay, so we have a smooth cubic threefold. We fix finite subgroups such that rank of the we don't need this condition because by Lesher's theorem rank of the Picard group is 1 anyway. But for singular one, I will mention singular cubics a bit later. We need this condition. Okay, action leads to P4, so basically we consider G is a subgroup of PGL5, and then we have this very simple theorem. 3 conditions are equivalent: G-birational rigid, G-birational super rigid, and we don't have a G-invariant planes, and G is not isomorphic to these 3 groups, and that's it. So particularly for cubic threefolds, answer to the color question is yes. And okay, why yes? Because this is basically, this was mentioned by Kohler in his paper, but this is actually easy exercise. So for G-birational super rigidity, this question of colors automatically has a question. So if you don't have, you can state it in language of Sarkisov-Lins. G-birational rigidity means you don't have any G-Sarkisov-Lins which starts on your threefold. So if you don't have them for the small group, you don't have them for the large group. But for rigidity, this is not exactly the same thing. So anyway, so this implies color question has answered yes in this case. Okay, and now basically let me briefly mention how to prove this theorem because it's kind of.
Sorry, you have like an example of a G and an X where it is G-birationally where the conditions do hold?
When G-birational, I missed them. Yeah, give me a second.
Okay.
Give me just a second. Okay. Yeah. So first of all, one direction. Okay, so first, okay, this clearly implies this. Okay, now let me explain that basically this implies this. So look, if P4 has a G-invariant plane, then as my only 2 slides ago, I can just project from the plane and I get a fibration to cubic surface. Done. So this condition we must require. What's the problem with these 3 groups? Why they bad? Okay, these groups are kind of special. There's not so many cubic threefolds which admits action of this group. Okay, let me just explain. Okay, before explaining what's wrong with these groups, let me just say that proof of this theorem actually based on classification of the automorphism groups of cubic threefolds. We know the full list. And this is not very long time ago. I don't remember, maybe a few years ago, 5 or 6. It's a paper by Y and U. So they basically describe all groups which can act on smooth cubic threefolds. So let me just basically list. So if you have a smooth cubic threefold, if you have a finite subgroup which acts on X faithfully, then it has to be a group, isomorphic to the subgroup of one of the following group. Automorphism group of Fermat cubic, this gives you a lot of groups. Automorphism group of Klein, this is Klein cubic, P set to 11. Or these four strange sporadic groups. For each of them, you can list cubic threefolds. I don't have space here, so I didn't do that. Okay, so for example, so basically now, using this classification, you can get a complete answer, and this answer is actually on the next page. So essentially, classification with equations and with groups. So Q smooth cubic threefold G-birationally rigid, if and only if, for example, first case, X is a Fermat cubic, and G is one of what we call plane free groups, exactly groups which doesn't live in variant plane. I list them on the previous slide. On the next slide, I will see them in slide 23 groups. And again, one exception is this guy. I will explain why. Plane cubic, and you have only two groups, A5 and this the full group. I must actually say that for this group, G-birational rigidity was proved long time ago. It's basically just a remark. It was very easy by me with Kostisha, my friend from Moscow. And basically, this was just a remark to paper of Proker. Proker classified finite simple subgroups of the Cremona group of rank 3. And in particular, for this group, this is a simple group. Proker proved that this group can act on only two Fano threefold. One of them is a Klein cubic. Another one is actually this Fano threefold of Picard 1 and degree 14. But Proker was not sure that they are not equivalently birational. So we basically wrote very simple remark explaining that Klein cubic is G-birationally rigid for this group. In particular, this two threefolds, this two threefolds are birationally isomorphic, exactly as I explained earlier, but they're not equivalent. So this was done long, but we don't need this system. Our proof is independent. Okay, anyway, and then basically this is a very strange cubic with a lot of with this group of symmetries, and you have few subgroups. Okay, and and basically X, this is basically like deformation of Fermat cubic. You just add this term and very explicit groups. This, and this. It's very explicit classification. So, and again, all these groups, it's not isomorphism clusters. They're actually unique up to conjugation. You can just leave the generators. I don't have time. Or you can use magma to find the generators. Okay, so this is the groups of on Fermat cubic threefold, and this is the graph of incident relations. This is the full automorphism group, and this is it. So basically, our project started with this graph, and essentially it's ended with this graph. So basically, the idea of the proof is like this. We first decided to try just one cubic, Fermat cubic, and just go through all subgroups. How do you go all subgroups? It's difficult, but now we have magma. And magma basically can list everything. Magma can list the generators, check conjugation. So magma produced this graph. And then, inspired by polar equation, we actually realized that we need only to check first for minimal groups. And minimal groups, you see, there's 1, 2, 3, and 4. So this one is a bad guy. We started from with this guy, and we proved that actually it's not G-birational. So, which is okay, but we were lucky. If you cut this node, you still have these three minimum. You do, because, for example, we were afraid if you remove this is bad guy. This doesn't give you G-birational rigidity, but theoretically it can influence, for example, this and that, but they contains other groups. Yeah. Okay, no, this two minimum. This is actually 2A5, but not conjugated. 1, 2, 3, 4, 5, 6. 6, okay. Fine. But this two I don't know. Okay, anyway. So, but later it turned out to be that essentially this graph contains almost all groups, regardless of the defining equation. Which is not actually surprising. Basically means that Fermat cubic contains most of symmetries of cubic 3. Okay, so as a strange side effect, when we proved this our theorem, basically when we proved this our theorem, we went through the proof. It was actually after we proved this. We went through the proof, and we look at the last case. You have this few groups, yeah, and this parameter here is this parameter is some bad value. Bad values where cubic is singular. But surprisingly, in singular case, our proof also works. We just need to check that condition that the invariant part of the class group is rank 1, but then we just check our proof almost line by line. There's almost all steps of the proofs work in the singular case. So in this case, we actually didn't need to assume that the cubic is smooth. And surprisingly, it also solves the problem for singular cubics, which is actually originally initiated by Artem Avilov, student of Prokhorov. He essentially proved that if a singular cubic threefold is G-birationally rigid, then there are very few possibilities. He said that either it's a gray cubic and the group is S6, A6, S5, A5, which are called standard one, lives invariant hyperplane, or some special 9-cubic threefold, and you have only these groups left. But and then Avilov basically proved that in this case everything is rigid, G-rigid, but in this case he didn't. So a couple years ago with Zhizhidrankovsky and Yurichenko, we proved G-rigidity for these two groups. So basically only this guy left and this guy left. But this is follows from our proof which I just mentioned. So again, it was totally unexpected byproduct. We just proved our theorem for smooth cubics, and then we just realized that it's also get rid of these two cases, this case and this case, without any almost no additional effort. Okay, so basically now we know all G-birationally rigid cubics, singular and smooth. Okay, so what's the problem with this? I listed 3 special groups. Why they're bad? Let me start with this 2, which is actually somehow related to totally independent project. It's called maximally non-factorial Fano threefolds. But anyway, so the idea is like this. You consider smooth cubic threefold with action of this. And then the representation theory tells you that representation should split as 1-dimensional and 4-dimensional. So essentially, it should be G-invariant hyperplane section. And you immediately, from classification of automorphism group of cubic surfaces, you deduce that this hyperplane section has to be smooth. And since it's smooth, you know these groups, very special groups, it has to be what's called closed cubic surface. It's a cubic surface whose automorphism group is S5, permutation of 5 elements. And from geometry of the surface, you know that this surface contains 2 lines. Essentially, the surface can be, with action of these 2 groups, can be obtained by equivalently blowing up the Lopez surface of degree 5. So in 2 points. So it means it contains 2 lines such that this curve is G-invariant. And then what you do, you construct a G-Sarkisov link, which is not Sarkisov. Namely, you blow up these 2 lines, and then you do the flops. 2 lines on smooth cubic surface, there are exactly 5 lines intersecting them. So you flop these 5 lines, strict transform of these 5 lines. And then after you doing this, after you did this, your surface, it's this flops, induce contraction of these 5 lines on the surface S, and your surface S becomes P1 cross P1 with normal bundle of -1 plus of -1. So you contract it, and what you get a Fano threefold very similar to the link which I described, anti-canonical degree 14, but class group is of rank 2. But in this case, invariant class group is of rank 1. So this is not Sarkisov link because this guy, its class group is not 1. Yeah, but it's actually a nice thing. So if you think about this, this is the generation of this smooth Fano threefolds of degree 14 with Picard rank 1. So you expect, when you get the node, you expect that your intermediate Jacobian drops. it was a 5-dimensional, so you expect it should go to 4. But instead of this, intermediate Jacobian still not Jacobian of a curve, but your class group jumps. So which is basically what Neil mentioned yesterday, is like a defect things, which observed by Clemens. Yeah, so this is a nice thing. So this is exactly this maximal non-factorial on the table. So we have one node and the defect jumps exactly by 1. It's important from derived mathematics point of view. Yeah. Okay, good. So this is explain why these two groups are bad. They're not G. Okay, next group. This is actually was fun. We was absolutely sure that this group should be like rigid. It's kind of nice, yeah. And we even proved this. We even had a proof that the cubic threefold with the action of this group. First of all, it's easy to see that in this case, cubic threefold is unique. There's only one cubic threefold which admits action of smooth cubic threefold, which admits action of element of order 11. It's clean cubic, and we had a proof modulo auxiliary lemmas. And one auxiliary lemmas was we need to sort out links which starts from blowing up 5 lines. And I said, sure, of course, this guy has no G-invariant 5 lines. And then we found. So we have 5 lines. You can see those 5 lines for configuration of curve of arithmetic genus 1 of degree 5. And once you see this configuration, you immediately remember the link, Sarkisov link found by Fano for the smooth quintic curve, quintic elliptic curve. This is a singular quintic elliptic curve. And this curve is G-invariant. And you immediately construct the same link. So you blow up your cubic in these 5 lines. So this is a singular guy. Then you do 5 flops, not ATF flops, bad flops, but anyway, it's okay. And then you contract a reducible surface, you get a smooth Fano threefold with Picard rank 1 at canonical degree 14, the same guy which described in the beginning of the talk. And but also you blow up here nodal, 5 nodal curve of arithmetic genus 1. So this is similar, but this is smooth and this is. So this is a new link. I was actually very happy because it's kind of the generation of the classical link by Fano, but it is new. So it's slightly different. Okay, good. Okay, now let's basically sketch of the proof. What is the proof? Of the theorem. So you fix only one direction need to be proven. So if you have a smooth cubic threefold and before a new group such it doesn't leave invariant planes, and you assume groups is not isomorphic to these 3 bad groups, then you have to show that it's G-birationality. If you show this, then this is done. So again, proof based on classification by Y and U, but implicitly you can actually, if we really wish to, we can partially avoid this. Because, let me explain why. We didn't, but if we wish, we could avoid classification. Namely, by the assumption that P4 doesn't contain G-invariant planes, it's basically mean that first of all, you observe that the group action really given by representation. So what I yesterday mentioned, Amitsur subgroup in this case must be 0. So G really leads to GL5. So we have representation. So you take this representation V5, and you by this assumption you have 2 choices. Either it cannot have 2 or 3-dimensional sub-representation. Otherwise, P4 would have a plane. So it means the representation either irreducible or it splits as 1-dimensional plus 4-dimensional, and you can twist that by the characters. So you may assume this is trivial. Actually, if you use this, it's much simpler to find the symmetries of it. Most of the papers of the YU deals with the cases when representation splits in much more ugly way. So to be precise, if we didn't have the paper, we would basically just start from this and found classification, but reduced classification only in this case. So it's possible to do, but we trusted the paper, so it's okay. It's simply true. Okay, so we have this representation choices. And in particular, it means that group cannot be cyclic or dihedral. Yeah, and then we basically see that. Okay, this is a mistake. This is not isomorphic. G is a subgroup of. Sorry, I actually was told to prepare this slide yesterday night. I didn't know that we don't have a blackboard, so there should be typos there. So it took me a while, yeah, especially to put these colors. Yeah. So anyway, so it's a G is a subgroup of one of the groups. So which, yeah. And now we just run magma. You just go through subgroups of this. We wrote a script. You go through the subgroups of these groups, and you check which one has 5-dimensional or representation or 4-dimensional faithful representation, irreducible faithful, yeah. And you might produce a big list, but this list, which we already knew, it was a plain free group section of Fermat cubic, but equation maybe not Fermat, but groups are the same. And these 3 groups claim, and these 2 groups, which I meant. Okay, and now basically what I said, you can just think about Kohler equation and you try to see the minimal subgroups of them which satisfy this problem. So we observed from the classification of groups that G must contain one of these three groups. 1, 2, 3, and 4 groups. One of these 4 groups. Yeah, A5 in the Fermat cubic case, it appeared twice because the action could be given by either reducible representation or irreducible representation. But as isomorphism, it's only one guy here. So to be precise, this is like one group, but really 2 different actions. So we have to deal with them separately. These 2 very small groups, yeah. And this is a relatively big group. Yeah. So if we, but the problem is that when you restrict representation to them, a priori representation may split in a bad, ugly way. So you theoretically cannot use this reduction. But using magma, we check that in each case, when you take your representation B5, representation when your group G acts on the ambient space, when you restrict to these groups, it also remains either irreducible or splits as 1-dimensional plus 4-dimensional. So, and then it basically means that if we prove G-birational, H-birational rigidity in this case, we sort of done. And we done it totally independently, so 4 different lemmas, 4 different sections of our paper. Proofs doesn't look alike. Of course, the main idea is the same, but technical issues are totally different in each case. So we just one by one proved rigidity in each case, and this is actually everything is done. Yeah. Again, I put here why, because as I said, Kohler equation for G super rigid property is positive part. We gave a proof in this paper just in case, but this is very important. Okay, so basically, then let me illustrate how to prove one of the lemmas. The smaller group, the more difficult. So to prove, and the proof becomes longer and longer. But we started with this group because it was the easiest one. And let me just explain how to prove. This lemma, this is a relatively big group, and the proof is actually very short. So you fix this group, and through representation theory, you basically see that if it acts on this cubic threefold must be Fermat. This is only one cubic threefolds with invariant with respect to them. Because in the given representation, because we know representation has to be in this case reduced, because it has no 4 dimensions. And this group is unique up to conjugation in the automorphism of Fermat. So we have it generators. And we need to prove that it's birationally, X is G-birationally rigid. We suppose it is not. Sorry, it's G. Sorry, G. Yeah. And then this is a class. This is an engine of Sarkisov program, an engine of G-Sarkisov program. If something not G-birationally rigid, super rigid, it means you have some Sarkisov link, G-Sarkisov link, which starts in it. It's automatically produced some mobile linear system on your X, such that singularities of this log pair, this scaling factor 2/n means that this guy is anti-canonical. Singularities are not canonical. This is absolutely standard in every similar problem it appears. As I said, this is essentially engine of Sarkisov program in this particular case. Okay, so we have to show that this is impossible. Okay, there's many ways how to show this impossible, but one way is very cheap and short, but it usually never works, but in this case it works.
Very good question. When you say suppose X, it's not H birational.
No, there's no H, it's a copy paste. G should be G everywhere.
This is perfect.
It's as I said, sorry, many
No.
should be typos. Thank you. Yes, many typos. All good. Okay. Good. So we want to yes. So this property is very nice. It has a global meaning. It exactly means there is no Sarkisov length. But unfortunately, being not canonical, it's not nice property of log pair from the point of view of minimal model code. We would much more prefer if instead of not canonical, I would put not log canonical. This would be very good because in this case, it means we have multiplier ideal shape and we can put all these big bombs on these things. But it's not true. But what very cheap observation. So if you multiply this guy by 2, it's going to be not log canonical. It's an exercise. You just read it's exercise. But this trick usually never works because basically we want to obtain a contradiction. But if you multiply this whole thing by 2 and you put here log, in many cases it's not big. You can construct example. But here it worked. So we multiplied, I call it multiplication by 2 trick. We got a new pair. And now we totally forget about the old pair. We just work with this guy. But it's a class in cohomology multiplied by 2, so it's actually not so good. Yeah, and then you do this thing, which is basically goes back to Kawamata and Shakurov. It's usually called tie breaking. I sometimes call it Kawamata-Shakurov trick. So basically, you want to have this log pair, but you want to slightly change it such it's slightly better. So almost the same, but slightly better. So namely, we first decrease this number a bit, such that singularities are strictly log canonical. Why we need this? In this case, multiplier ideal give you a reduced subscheme. It doesn't matter, but psychologically, it's actually maybe it's better to work with a reduced subscheme. After, not only psychology, because if your pair has low canonical singularity, but not chromatic, there's a notion of low canonical centers, they behave well. Intersection of low canonical center is a low canonical center, which is not true if singularities are not low canonical. So this is actually really need this. But then we do this tiebreaker. We choose a minimal low canonical center. It's exactly means image of exceptional divisor with log discrepancy 0. Or it's not log canonical, so it should be some divisor. So we take the minimal center, minimal in the sense of dimension. Like in this case, it's actually a point or a reducible curve because the linear system is mobile, it's no surface. And we take its orbit, so now this is G-invariant guy. So we have these two choices, but we want for some reason, we want to get rid of all other centers. We want that this is the only places where this log pair is not log canonical. And this is exactly what can be done by tiebreaker. Essentially, it means you slightly perturb your boundary, and you add something, and you subtract some, you decrease some coefficient, and all other centers disappear. This is very absolutely standard in a minimal model problem. So again, you replace this two number and this linear system by some number slightly less.